Hello there, welcome to a video on Albatross UAV flight test briefing. This video will explore the preliminary test and assessment carried out on the aircraft to ensure its safety and optimal performance. This video covers the weight and balance test, center of gravity position, flight controls test, wind tunnel test, and other crucial aspects of the aircraft's stability and maneuverability. The initial test to be conducted is the weight and balance test. First and foremost, understanding the impact of CG position on aircraft stability and maneuverability is crucial before setting it. Placing the CG forward will increase stability but reduce maneuverability, while placing it aft will decrease stability but enhance maneuverability. Thus, defining the mission objective of the UAV is crucial. For instance, mapping missions require a highly stable UAV, while racing UAV needs the UAV to be extremely maneuverable. Furthermore, it is crucial to comprehend the significance of the terms statically stable and dynamically stable, as they will be frequently referenced throughout the video. By analyzing the wheel reaction forces and respective loads around the CG, a range of 15% to 40% of the mean aerodynamic chord (MAC) was estimated as the appropriate center of gravity position range to achieve aerodynamic stability. As mentioned previously, it is important to consider the mission objective when selecting the appropriate CG position within the recommended range given. Additionally, it is worth noting that the neutral point is approximately located at 50% MAC, and for flight testing purposes, the default CG position is typically set at 35% MAC unless specified otherwise. Next, we will proceed to the thrust test. Following the weight and balance test, a thrust test was conducted to determine the linear relationship between RPM and sea level thrust. This information can be referred by the pilot during a mission, such as during takeoff. The maximum level thrust achieved was 28 newtons, and the relationship can be viewed in the accompanying graph. Moving on, it is important to double check the inputs before flying during static control response tests to prevent accidents and damages to the UAV. The elevators need to be reversed. The ailerons also need to be reversed to provide a roll right and roll left. The rudders need to be reversed to provide a yawing motion in the left and right direction. The deployment of the flap should be checked in the up and down direction. Finally, the thrust needs to be checked for throttle up and throttle down. The next phase of the testing is the dynamic control test. For the purpose of this experiment, we will mainly be focusing on the live grapher, displaying elevator input and the angle of attack for accurate monitoring of the aircraft's behavior. To further explore the relationship between wind speed and the aircraft's response to elevator input, the wind speed was increased incrementally. It was observed that the pitch response is more sensitive and quicker at Vmax than at Vstall. This change can be observed graphically. As the wind speed is increased, the angle of attack response due to the elevator input produces less to no oscillation. Hence, it was concluded that higher wind speeds will result in a more responsive aircraft and quicker attainment of stable angle of attack. After extensive testing and data collection, it was determined that the optimal CG position for pitch control is around 30 to 35% of its MAC. However, it is important to note that the aftmost CG position at which acceptable pitch control can be maintained varies depending on the aircraft's design and must be determined through further testing. The aircraft's lateral response were next evaluated through its rolling characteristics using ailerons. The test measured how the roll rate for a fixed aileron input changes with change on wind speed. It was found that the steady roll rate increases with wind speed. The test also verified the rudder deflection gives an angle of side slip of the correct sign. Additionally, the damping and pitch was compared to the damping and yaw, and the damping and yaw was observed to be greater than the damping in both roll and the angle of attack. During the test varying a range of CG vertical positions, it was observed that increasing the vertical displacement of the CG increases the magnitude of the nose-up pitching moment. It was also observed that increasing thrust amplifies these effects, further intensified the pitching moments associated with changes in vertical CG position. Next, the data of the flight performance characteristics of the Albatross UAV will be presented based on the static wind tunnel test results. Firstly, let's take a look at the lift curve slope for different flap settings. As can be seen, the CLmax for the Albatross UAV is 1.2 and it occurs at an angle of attack of 15 degrees. Next, let's move on to the drag polar. It can be seen that the drag increases with the increase in lift coefficient for all flap settings, which is expected. For the glide ratio against the CL plot, our aircraft predicted the best lift of a drag to be around 15, occurring at a lift coefficient of 0.6 for a flap 40 degrees. However, when we compare this value with the manufacturer's sales data, which claims the best lift to drag ratio to be around 30, we can see that they don't agree. Moving on to the longitudinal trim test results, CM vs CL was plotted for different elevator inputs and the results are as follows. The recommended elevator angle is the angle that corresponds to the point where the CM vs CL curve intersects the 0 lift line, which represents the angle of attack at which the aircraft is neutrally stable and requires the least amount of elevator trim to maintain the level flight. It was observed that the recommended elevator angle to trim for best performance at the default CG location of 35% MAC is between the grey and blue line, as can be seen in the graph, which corresponds to an angle range of 0 to 15 degrees elevator. Finally, for the longitudinal stability test results, CM vs CL for a range of CG locations was plotted to estimate the location of the neutral point. The neutral point is the point where the change in pitching moment is independent of the angle of attack and hence the CL. This can be shown as a horizontal line on the graph. Based on this, the estimated location of the neutral point is around CG of 0.1, which is 10% of its MAC from the leading edge. Next is the free flight test. Starting with the ground handling test. The combined nose gear, steering and rudder input were verified to provide sufficient authority for maneuvering the aircraft on the ground. During taxiing, it is important to maintain a low speed and avoid turning too fast, as excessive steering input can lead to a loss of control and even cause the aircraft to flip. Therefore, it is recommended to exercise caution and adhere to safe taxiing practices to prevent any potential accidents. The recommended taxi speed is 10 meters per second. Moving on to the minimum unstick speed test, it was evaluated that the minimum speed needed to achieve wheels off the ground with and without flaps deployed. The results show that the takeoff speed with and without flaps deployed was around 16 meters per second at a takeoff mass of 7 kg. These results also took into account the stall speed of 10 meters per second. The cruise trim test was conducted to identify the elevator trim setting and throttle setting required to achieve steady level flight at a cruise speed of 20 meters per second. It was found that the required elevator trim setting was negative 2.5 degrees and the required throttle setting was around 20 rpm. Finally, the maximum trim level flight speed was determined to be around 55 meters per second at an altitude of 640 meters. The minimum trim flight speed was around 25 meters per second at an altitude of approximately 20 meters. The phagoid oscillation can be simulated by trimming the aircraft for level flight and applying an elevator pitch-up moment input, followed by releasing the input. During the oscillation, the angle of attack remains constant, while the attitude and speed of the aircraft fluctuates. The success of the simulation was verified by the live graphing as seen. The period of the oscillation was later determined to be 15 seconds, corresponding to a frequency of 0.067 Hz.